Mr. Redwine just left, so, we
That's
can start
okay.
when he gets back.
Yep, we can wait for him to pop back in.
Hey, maybe. Okay.
We're recording now, too.
Excellent. So I'm not sure what was going on. It said something about a firewall, and hopefully
We'll roll with it. Yeah.
Indeed. All right. So I'm ready whenever you guys are. Just tell me what to do.
All right, let's start. So we're recording. All right. Good morning and welcome to Haas Hall Academy in Bentonville, Arkansas. We are happy to host a debate today on the following topic: is the Earth older than 47 million years? My name is Rayan Sharif and I will be serving as the moderator. Arguing the affirmative will be Mr. Adam Redwine, a nuclear engineer at Ben Gurion University of the Negev in Beersheba, Israel. Arguing the negative will be Mr. Pete Golden, an instructor here at Haas Hall Academy. Each speaker will receive 20 minutes to make his case, and then we'll have 10 additional minutes to elaborate or respond. If any live attendees have questions for either speaker, you can type them in the chat if there's time at the end. Gentlemen, do you have any questions for me?
No.
No.
All right then. Mr. Redwine, if you are ready to present, time will start as soon as you begin.
Okay. Can you see my slides?
Yes.
Yes. Okay, then I will begin. So, my name is Adam Redwine. I appreciate the opportunity to speak to you all. I do have a lot of material, so I may be pretty quick, but hopefully we'll clarify in the rebuttal if necessary. So I grew up on a farm in western Iowa. This is my hometown, Sioux City. Ended up with degrees in physics and nuclear engineering from Louisville, Kentucky, and Texas A&M, respectively. I spent 8 years as an engineer working in special nuclear materials. That really means nuclear weapons material in military reactors. I left that a couple of years ago and went back to school, where I am now a PhD student in the Department of Nuclear Engineering here in Israel. My degree will be nuclear engineering, but the work I'm doing is actually experimental physics. So that's my field and background. Now, the first part of my presentation, actually, I'm going to talk more generally about physics rather than the specific topic at hand, and hopefully addressing one particular key point that I think is really important to this discussion. So, big picture, what do we do in science and physics in particular? Well, the world around us appears to be consistent, or at least it seems to be this way. When we do experiments, we get the same results day to day, and we can use mathematics to describe that consistency. So, for example, if we have a couple of apples, we add 2 more of them and count the total, we see that we have 4 apples. So we can use symbols like the number 2 and this plus sign to capture those concepts of addition and quantity and equality. And then we can build what are called mathematical models. Now, the nice thing about mathematical models is that they can apply much more broadly than just this one specific instance. And also we can use the rules of mathematics to make predictions about what we would expect the real world to do. Now, building a model is a challenge, but a lot of people have done it over time. And so in order to decide which of those models we prefer, we have to have some criteria to judge them. So I'm going to walk through 3 criteria that are used for judging scientific models. One is explanatory power. So the goal of science in general and physics in particular is to explain the world around us. We want to have an explanation for why things behave the way that they do. And really more importantly, even, we want to be able to predict how things will behave in the future. Now, giving competing models, you want the one that's going to explain more things and more varied things. Also, models should explain everything that's already explained plus more. So, for example, historically, Aristotle was a philosopher back in ancient Greece. He developed a model that explained falling bodies. He said, when you let go of a stone, it falls to the ground, and this is why. Now, much later, a guy named Isaac Newton came along, and he explained falling bodies, but he presented a model that explained falling bodies and also explained planetary motion. So his model incorporated the explanation for falling bodies, or at least incorporated this phenomenon, and then provided more in addition. Now, eventually, a guy named Einstein came along. He presented a new model, and it explained both of these things, falling bodies and planetary motion, but it also explained observations about the speed of light. So we have this sort of increasing coverage of the model. Another criteria that we use to choose among models is called parsimony. This is a fancy word for a concept that is ironically a little difficult to explain, but parsimony means simplicity. So in the case of mathematical models, we can have lots of different kinds of simplicity, but I want to walk through a specific example to hopefully to clarify this. So positions of stars and planets are things that can be measured. You can take an astrolabe, you can go outside and measure the distance from the horizon to a star. And if you do that consistently, time after time, you take good notes, you collect some data that you can then use to help develop a mathematical model. One person who did this was a guy named Ptolemy. He developed a model that had Earth at the center and then put the moon and the sun going around the Earth, obviously. But he also had what we would call planets, but they would call wandering stars, going around the Earth too. But in order to make the mathematics work, he had to add in these extra circles that they called epicycles. So this was just a necessary feature to get the mathematics to turn out right. And you can see down at the bottom here that there's no way that you can make a model like this with fewer than 26 variables. It just doesn't work geometrically. Now, we used that model for about 1,000 years. It actually was pretty decent. It wasn't perfect, and we knew it wasn't perfect, but it was the best we had until a guy named Copernicus came along, presented a new model in which the sun was the center, and then he had all of these wandering stars or planets going around the sun, with the exception of just the moon goes around the Earth. And he could explain this phenomenon now in 16 variables. So it was a simpler model, and it actually gave better results. So a little deeper into parsimony, it can represent this just fewer equations of variables. That's one aspect of parsimony, but it also appeals to a more general sense of simplicity. So Isaac Newton's models for mechanics, for how the world works, are actually relatively simple. Some of you may have taken physics and may disagree that Newton's physics are simple, but on the grand scheme of things, they actually are. But they have a big problem, a philosophical problem, and that is that they incorporate what are called fictional or fictitious forces. Now, these forces account for the observer's perspective and movement relative to the experiment at hand. You have to add in not just a factor to explain this, but you actually have to change the underlying meaning of the model. You have to say that there is this force dependent on the observer, which is really a big problem. A guy named Lagrange used Newton's ideas and came up with a new way to do things. So the result that you get using Lagrange's mechanics are basically the same as what you get through Newton's, except they have this advantage that everybody agrees on what the rules are. A person watching an experiment from a train and a person standing in a field doing the experiment, you all agree on what the result's going to be using the same rules. Now, one more criteria for choosing among models is called consilience, again, a fancy word. It means just this top bullet, that if you have competing claims, you want independent lines of reasoning to all point to the same conclusion. Now, when considering something like the age of the Earth, we have a whole bunch of things that all have to be explainable within the model that's being used. So things like distances to stars, solar observations, continental drift and geology, presence and location of radioisotopes, just all sorts of things. And if somebody presents a model, if they say, I believe the Earth is X years old, or more than X, or less than X, hopefully they can give you a mathematical model. I mean, that's how science works, is we have these models and we use them to make predictions. If they present you with their model and say, this is how old the Earth is, you need to be able to use that model to make predictions, not just about the age of the Earth, but about all of these other things too. So what about modern physics? Where are we and what models do we use? So modern physics has basically two models, and these cover pretty much all known observations. One is called relativity. This is Einstein's model, and it covers things that are big and fast. So this is mostly like stars and planets and things going close to the speed of light. We do actually apply it to small scale things too, but that was really where it was formulated, was with these big and fast things. And then the standard model of particle physics, which really covers all of the small stuff. So this is things like electrons and neutrons and protons, and how do atoms form and split apart and all of that kind of stuff. So we basically have two models. Now, relativity is particularly interesting because it places time and space within the context of the theory itself. So in Newton's model, time and place are universal. They're like a stage. So everybody in the universe agrees on where and when something happens. Now, they may have to make adjustments for their motion to some extent for the results of the experiment, but they all would agree that these two billiard balls hit each other at this particular location at this particular time. Now, relativity does away with that. So in relativity, you actually have to account for your own motion relative to the thing that's being observed, but it maintains the Lagrangian characteristic of being universal in terms of rules. So the actual mechanics of relativity are the same for everybody, even though the actual result that you get at the end of the day does depend on the observer. But given this, time and space themselves become variables in a coherent set of equations that describe all of reality. So these models are firmly within the branch of mathematics called geometry. So I'm going to talk a little bit of geometry. Now I put this little figure over here on the right. You can imagine this extending indefinitely to the right or left with these sort of inverted triangles. And I'm going to use this to talk about symmetry, because symmetry is an underlying guiding principle for both relativity and the standard model. And there's lots of different kinds of symmetry. So we could, for example, draw this green dotted line and rotate this whole thing 180 degrees and say after that rotation, it looks just like when you started, even though it underwent a transformation. So we would call that a rotational symmetry. You could also say there's like a translational symmetry. So draw these green dotted lines and you move the whole thing a unit to the right or a unit to the left. And again, after the transformation, it looks just like it did when it started. We could, for example, identify reflectional symmetry. Draw this dotted line, and no matter how far you go in either direction, to the right or to the left, and you look at what you have, it's going to match up on either side. So this is a reflectional symmetry. Now, this is particularly important because in the Lagrangian framework, we can identify symmetry in time. So we can start a stopwatch and say that when the stopwatch hits the top, that's t0. And then we can look forward or backward in time. And it turns out that the laws of physics that are related in that time symmetry through the conservation of energy, meaning that conservation of energy is mathematically identical to symmetry in time. Because of this, we can directly observe today that the laws of physics were not different in the past by testing the conservation of energy. So if somebody says to you, I think the laws of physics were different in the past, I wasn't there to see it, what they are telling you is that they do not believe that the conservation of energy is a good description of the universe. All right, so to the topic at hand, radiometric dating. Radiometric dating is the discipline that we use to determine things like the age of the Earth. I pulled a textbook out of my university library and went through the index. This is kind of got an old one. This is a 30-year-old textbook. And you can see there's a lot of different methods here. So I'm only going to talk about one particular method and actually only use data from one particular paper, but this really is a broad discipline. And radiometric dating as a discipline is complex. So it's true that we observe decay rates, but we actually also calculate decay rates using the standard model. So physicists like me, we go and we use the standard model to calculate a decay rate, and we do so using these underlying variables, things like the coupling constant, nuclear matrix elements, etc. These are really the things that we're looking for when we're doing physics experiments. We're not looking at decay rates in and of themselves as fundamental properties. We're looking at these underlying variables. Now, changes in these values impact decay rates differently, which is particularly important when considering things like the age of the Earth, because, and I'm not going to get too deep in this, but there are 4 different decay series, so 4 different chains through which elements can decay. And one of them that we're going to use is the actinium series. This has uranium-235 eventually decaying into lead-207. Now, there are 16 different decays along this chain, and they are not all the same kind of decay. So some of these are alpha decays, some of these are beta decays, and those decays are affected differently by these underlying phenomena. The uranium series incorporates uranium-238, eventually leading to lead-206. There's an active community of practitioners in these methods. They publish regularly. You can go find them at university libraries. Unlike creationist journals, there's no statement of faith. Anybody can publish. All they have to do is present new findings and pass peer review. So what does the science tell us? What do these models that we use tell us? Well, in my rebuttal, I'm going to go through actually how we get these particular equations. But this is the prediction of basically standard physics, accepted physics. This is called a parametric plot. So you have an x-axis that represents one equation here, this upper equation, and a y-axis that represents this other equation. And you can see with here, the only variable is t, is time. So 1 is a number, e is just a number, mathematical constant. These lambdas are the decay rates, which I assert are almost certainly constant. And then t is time. So as you increase time, you move along this blue line. And here's a few markers for you. So this is 1 billion years, 2 billion years, 3 billion years. Just for reference, 47 million years is here. This is this yellow dotted line. So if Mr. Golden is correct, all observed data in the real world should lie between this y-axis and the yellow dotted line. That's where we should see real data if the Earth is less than 47 million years old. So when we go out into the real world and measure these values, what do we see? We see this. So this is data that I pulled from one paper published by Jones in 2020. Now this data was collected from rocks that were picked up all throughout the Alaskan Western Range. Put up that prediction again. So the blue line here is predicted, purple is observed. By the way, there were actually a few values out here that were higher. I removed them just because I thought this was a prettier aspect ratio to look at for this figure. But this is where real data lies. So new models replace old ones. Remember, Ptolemy's model was used for 1,000 years before it was replaced by Copernicus's, and Aristotle's physics were used for even longer than that. We don't replace a model until we have something that's better. But good scientific models, they make testable predictions. So this blue line, the exact solution to this was actually known in about 1907. So that would be people riding around in horses and buggies before World War I. A good physicist could have drawn this blue line for you with just a very small amount of information. They could not fathom the technology that it would take to get these purple dots. So you have to be able to make a prediction with your equations. That's what science does. We predict things and then we go observe to see if that prediction was correct. That data that I just showed you, that was from one paper, and there were, just for reference, 1,400 peer-reviewed papers on just uranium-lead datings of zircon between 1973 and 2014. Now, I'm not saying that that's, that necessarily means that this has to be correct, but think about that. 1,400 peer-reviewed papers. This is thousands of scientists who do this as a discipline, who their day in and day out is studying these phenomena. And Mr. Golden would have you believe that every single one of those people is misunderstanding their fundamental career, or they misunderstand the basic science of their discipline. Now, good scientific models explain everything that we already know, plus more. Any replacement of the current model has to make predictions about things that haven't been taken. So if you want to replace the standard model of particle physics, it's not enough to just say, oh, there's something wrong here, something wrong there. In fact, we know that there are some things wrong in the standard model. That's why we still have physicists. That's what I do. I go into a lab and look for things that contradict the standard model. That's my job. But that's not enough. You have to actually give us a mathematical model that makes predictions about things that haven't been seen yet. Give us a mathematical equation and let's see if 100 years from now we can use technology that you can't imagine and come up with data that fits it. We also have to fit all of these other radiometric dating methods and thousands of observations across all of these disciplines. So again, there's tons of different dating methods, and the decay rates are variable dependent on those underlying features. So if you want to say decay rates aren't constant, okay, fine. Not only do you have to come up with a model, you have to come up with a model that fits all of the decay rates of every kind, not just these one particular ones. And I did want to leave with a photograph here. This is actually the black point here is a star that's been occluded or sort of blocked out so that you can see it. But this bright spot here is actually a planet in the formation stage. So this is the first photograph ever taken of a planet. There's actually been more since this. It was 2018. But I thought that was pretty cool. And since I actually have a little more time, I'm a little surprised. I want to show you what the standard model actually looks like. So Mr. Golden, if you reject the standard model of particle physics, so this is the standard model Lagrangian, so this is the thing that you plug into that equation, which part of this do you not agree with? And how would you change that? I would love to know. Please do tell us. So that's what I have for my opening statements.
Thank you, Mr. Redwine. Mr. Golden will now receive 20 minutes to argue the negative.
All right, thank you. Let's get myself set up here. And let's explore Woo. Well, I'm going to start out by going down by 2 points here. I'm going to concede 2 points to my opponent. The first, can you hear me all right, Mr. Sharif?
Yep.
Okay, good. The first is that, yes, my view is vastly in the minority, all right? So I concede that, and that if I am correct, if my position is correct, then yes, I'm not only insinuating, I'm declaring that a large number of very highly trained, intelligent people who are experts in their career do have a misunderstanding of their field. So that's a bold claim, and but even a blind squirrel finds a nut every now and then. I'm also conceding the point that my opponent is more qualified than I am to speak on these things. Nevertheless, since we're all here, I'm going to go ahead and proceed with my points, and I'll let the viewer decide if what I say makes any sense or not. I don't reject the standard model. Excuse me. Sorry, I've got a Egg McMuffin that's stuck here. I do agree with his notions of parsimony and, pardon me, and consilience, that those are important. And I hope to show that there are quite a few dating methods for the Earth, which is our topic here today, that are quite simple, and that if we take them at their face value, they provide evidence for a young Earth. I do agree that it's very important, if I may rephrase the idea of consilience into simply the phrase, ideas have consequences that must be dealt with. And he's pointed out that if my position is correct, it would have consequences across many disciplines. And I don't dispute that either, but I hope to show that what's happening is that scientists, being human, interpret data through a framework. So Mr. Redwine did a great job of showing over 3,000 data points that I'm going to take a look at in a minute. And those were interpreted through a framework, okay? And so it's unavoidable, okay? In other words, if I plan a trip to Montana, I don't double check to ensure that Montana exists before I go. I take others' word for it. I'm assuming that it's there. There's a framework of knowledge that I have that's been given to me by other people, and I act on that. If I get to Montana and I find that it's not there, well, then I'll start investigating. But we all have a framework in which we interpret the data. And so I hope to show you some data points that create a different story than the one that is admittedly predominant in our world today. So I'm going to get right into that. I did want to look. Mr. Redwine was kind enough to forward me that data set from Alaska. So I wanted to look at that. So I'm going to move over to my desktop so I can pull that up. Okay. And I'm going to present now. Let's see. Go. There we go. Okay. So I'm just going to unpack the data he sent me here. Let's see. I think this is the one I want. Yeah. So here's the data points. So what happened was these guys went to Alaska, and there was a problem, a geological problem that they wanted to collect some data on to unravel. And that is, there are two formations, two terrains, we would say, of interlocking layers. And they wanted to know from which, there were two geological formations nearby, igneous rocks that come from molten lava, that contributed to this formation. The formations are now in sediments. And so one igneous rock was dated stratigraphically, I might add, to be much older than the other. And so what they said was, if we want to find out where these sediments came from, let's run some radiometric dating on them, and then we can assign them, and we can figure out, did they come from the north or the south, right, basically. So the point of this exercise was not to verify the blue line that Mr. Redwine showed us. The blue line was already assumed, and the blue line was used to date the rocks, the zircons, for another purpose, okay? So there's nothing wrong with that, but I want to show you that there's a framework involved here, a pre-assumed framework. So if we just look at these categories, right? So what they would do is they would take these zircons, these little crystals, and they're looking.
We can't see the data that you're presenting.
Oh, I'm sorry. Let's see here. Thank you. That's important, huh? Okay. Well, I'll get it in a minute. Okay. Let's try again. Okay. How about old dog and new tricks, Mr. Sharif? Let's see here. Okay. Almost there, I think. Well, now let's see what you can see. Okay. Oh, I know what I can do. I'm sorry. Okay. My entire screen, that's what I need to do. Okay. Okay, I think we're rocking now. Okay, here we go. So here's the data that he sent me. So what they're actually measuring, right, he pointed out, was varying concentrations of lead and uranium isotopes, right? That's the actual observation, okay? That's the thing that I can't argue with, all right? And they're reported up here, okay? So as we go along, we get these different ratios, okay? We get this thing that says error correlation. I'll talk about that in a minute, okay? Then we get the age, right? Well, the age is, of course, not directly measured. It's impossible to directly measure an age, but you can say, well, if you're not going to say it's that old, then why does it look the way it does, right? But just to be clear, this is not an observation here. This is an extrapolation or an interpretation of the observations, which are the isotopic ratios, all right? So we go on over here. It lists some uncertainties. That's fine, okay? Then it says the preferred age, okay? So the preferred age means that what they're going to do is they're going to look at several different ratios, and they're going to see which one fits the blue line best, okay, for that particular sample. That's the one that's going to go on Mr. Redwine's diagram. We see preferred age concordant scans. What does that mean, preferred age total scans? It means that they do multiple scans for the ratios on each sample, and only those that are concordant, that is, that are within an acceptable range that approach Mr. Redwine's blue line, are accepted and tabulated, okay? Now, all this is not nefarious. This is not a conspiracy. This is a perfectly legitimate way of doing things if you start out with an underlying assumption that the blue line is correct, okay? My point is that this whole exercise, this whole set of data points is not to verify the blue line. It is using the blue line to date the samples. That's what they were interested in doing. Okay. I'm not, for the sake of time, I could pull up the metadata. There's, they have to use an established titanite sample, a reference sample, to calibrate the machine. And that sample already has an assumed age of over 1 billion years. Okay. So, this is what I mean by a framework, all right? So it's not a question of, hey, we went out, we collected 3,000 crystals, and in a vacuum, we did data, and the data all correlated to our blue line, okay? That's not what happened. Is they recognize that things can happen, that over 1 billion years, right, or more than 1 billion years, no geologist is going to say that, that it's impossible that things could come in and affect the ratios, right, that they're using to date. So what they're going to do is they're going to try to use many samples to show a correlation, to show a strong correlation, okay, that can be extrapolated back. But anyway, that was just my point, was that there is a framework at work here, and there were actually, I mean, look at some of these. Here is one scan out of 172 was a concordant scan, okay? And so they deemed that one to be, it was a good fit. In other words, it wasn't messed up, all right? So there is some assumptions that go in. This is not just a case of purely raw data that lends this. Now, again, to save time, I'm not going to, that was just my point of this. I'm not attacking the veracity of this study or even the good fit of the line, okay? But I do notice that my opponent mentioned when he showed you that graph that he said that he's asserting that the decay rate was constant, okay? So that was used, that assertion was used to date the reference sample that was used to help calibrate the machinery that did this. So we can see that one idea builds upon another. And let's see here. So let's see. I think that's all I'm going to say about this because I hamstrung myself here with my bumbling on the screen. But let me go back to the table here so I don't run out of time. Let's see. I can figure out what I'm doing. There we go. Stop sharing. There we go. Okay. So I do hope to present some evidence that that decay rate is not necessarily, let's see, there we go. Can you see me again, Mr. Sharif? Unfortunately. Yeah. Okay, good. I've been doing this for a year and I still can't figure it out. So what I did was I brought some clocks here. I've got a clock, right? And I say, how long has this clock been running since midnight? You'd have a pretty good idea, right? Based on your previous experience with clocks, based on the observed rate of change of this clock right now, and based on the likelihood that I had reason to mess with it, right? Here's another clock. This candle, okay? How long has the candle been burning? What if I told you it's been burning for 4 years constantly? Well, you couldn't prove me wrong, but there'd have to be a lot of other stuff happen, right? I mean, we've got a ceiling up here. So the candle would obviously have to start out, if it's been burning at this rate, it would have to start out a whole lot higher than the ceiling. I've got a rock here. This rock is a clock, okay? So this rock is doing exactly what Mr. Redwine showed us. It's uranium turning into thorium, and each one of those is a uranium turning into a thorium back here behind me, uranium turning into a thorium, and releasing an alpha particle, or what we would say quickly becomes a helium atom. So uranium is releasing a helium atom to turn into thorium. This is the clock that is used to date many rocks, and when we're talking about the age of the Earth, it's funny, the age of the Earth is actually dated from meteorites, not from the base values that we get. If you Google how old's the Earth and it says 4.4 billion years or whatever, those are from meteorite samples. So the assumption there is that, well, the meteorites are in the solar system. Surely the meteorites aren't that much older than the Earth, and I would agree with that. And so if they're 4.4 billion years old, then maybe that's a reasonable assumption for the Earth. But what we're doing here is we're measuring, right? We're assuming how much lead or thorium, okay? Eventually the thorium makes it all the way to lead, so if I can get out of the way. We're measuring how much melted wax there is, if we want to use this analogy, how fast the candle's burning, right? You just heard how fast this uranium was going off. And that's what we can use to figure out how old this is, right? If we wanted to. But if the candle isn't burning at the same rate, then our assumptions might be incorrect. In other words, if I said this candle has been burning for 40 years, okay? And in the past, though, okay, in the past, it only burned a millimeter of wax every week, right? It was burning at a much slower rate, okay? Well, then that would fit our observations of a small candle. We could start out with less, okay? Now, getting back to Mr. Redwine's concept of parsimony, the simplest answer is the best. So is it simpler for me to say, well, the decay rates must have changed? No, it's not. Okay, so why do I do it? I do it because I have some other clocks, right? I have some other clocks that I want to look at real quick if I can. And if they contradict this clock, then I'm free to choose them over it, okay? So what are some of these clocks? Very briefly. Salt is deposited in the ocean every year, okay? It rains on the continents, and salt is sodium is very soluble. So when I say salt, I'm specifically talking about sodium ions. And sodium is very soluble in water, and it flows down the rivers, and it goes into the ocean, okay? When the water cycle continues and water evaporates out of the ocean, it doesn't take the sodium with it. The sodium can't evaporate. So we can measure, or we can estimate at least, the sodium influx levels into the ocean. And to my knowledge, there's no good explanation of any sodium outflow models, okay? And so the sodium levels, if the Earth is anywhere older than 10 million years old, should be much, much higher than we see them. It's a different sort of a clock based on the same sorts of techniques as this is. You're just measuring a rate, and you're measuring an assumed starting point, and you're measuring an observed ending point, so to speak, and then you can extrapolate backwards. So that clock yields a much younger age for the Earth. Similarly with sedimentation, okay? Sediment, sand and mud is also washing into the ocean, and the continents are being eroded. If we extrapolate current rates back, we get a younger Earth. Recently, there's been a lot of discoveries of dinosaur soft tissue, okay? So that's not really a clock, but it does set sort of a maximum limit, kind of like the ceiling set a maximum limit on the age of my candle here. We're finding out that proteins and collagens from fossils that are supposedly 65 million years old or older are being preserved. That shouldn't happen. Therefore, I would say the fossils are not that old. Earth's magnetic field that we use to operate a compass. We can measure that it is declining in total energy. And if we extrapolate that backwards, then we would get a much younger Earth. In other words, if we extrapolate it backwards, then we would get a magnetic field that becomes too great for the Earth to even exist. That's another clock. I'll have to save a couple of these for my rebuttal because I think I'm coming up to the end. But it's interesting. I mentioned that uranium becomes helium as it turns into thorium, or at least it gives off an alpha particle that becomes helium. Well, what happens to that helium? In other words, this guy's making helium right now, Okay. Well, the helium on the edges can float up. The helium inside the rock has to weasel its way out. We can measure the rate of weaseling, the rate of diffusion of helium. Okay. And that also limits the time. All right.
Thank you, Mr. Golden. Now, Mr. Redwine, you have 10 additional minutes to use as you see fit.
Great, thank you. I will share my screen again. And I believe I'm sharing, so if I'm not, let me know. Okay, so I do want to address several of the points that Mr. Golden just made because I think they're important, but more importantly, actually, I want to address his issues with the dating method that I have presented. So he's raised a couple of questions, and they're to completely honest, they are actually very good questions, and they're questions that scientists have thought about for a long time and have addressed specifically because they are good questions. I am disappointed that Mr. Golden didn't bother to look up the answers before the debate, but maybe next time he'll have some answers for us. So one question, how much lead was there in the crystal when it was formed? That's a great question. We have to know. If we're going to use the amount of lead as part of the ratio, as part of the dating method, how much lead was there to start with? Okay, so great question. The testing that we do is performed on zircon. So zircon is the chemical composition here. It's very hard, harder than steel, has a very high melting temperature. It's actually hotter than lava. You could throw these things in a pool of lava on the surface at least, and it wouldn't melt. That's pretty darn cool. But you can see the chemical structure over here on the right. The purple spheres are the zirconium. And the zirconiums form in these dodecahedra, and the way that these things form, or the thing that's driving this formation, is a parameter of the element that's called electronegativity. Now, the electronegativity of zirconium is about 1.33, and we know from observation that this zirconium can be replaced by other elements. So it can be replaced by hafnium or uranium or thorium. And if you look, I've written down the electronegativity here of these things that we know can replace zirconium, and the electronegativity in all these cases is very, very close. But how about lead? The electronegativity of lead, 2.33. It's really far away. So just like by the books in the theory, what we know of chemistry, lead does not replace zirconium in zircon crystals. It just doesn't work that way. That's not how you would form this particular chemical compound. Now, that doesn't mean that it's totally impossible. Theory is great. Sometimes theory is wrong. So we need to check. We're scientists, so let's go do an experiment. In 1997, a guy named Dr. Watson, he went to test this. He said, okay, well, maybe we're wrong. Maybe zircons can start with a bunch of lead in it. So what he did was he grew a zircon crystal in a pool of molten lead. So he had this pool of 66% lead oxide. Because the melting temperature is so very high, you can actually grow these crystals in liquid metal. He did that, and then he tested the resulting crystals for lead, and he found that the amount of lead was less than 1 part per million. So the amount of lead that we start with in a zircon is 0, or very, very close to it, because that's how chemistry works. Now, there's other questions. So Mr. Golden also raised the possibility that maybe we've made an adjustment that's wrong, or maybe there was a gain of uranium or a loss of lead. Now, mathematically, those are the same thing, because all we're looking at is this ratio. So we can say, well, what if that is the case? Maybe there was a bunch of lead lost or a bunch of uranium gained. What we can do is then correct for those changes over time. So if what we see today is the result of a bunch of lead loss or a bunch of uranium gain, then we make a correction. And then what we say is, okay, so now these purple dots are what we really should be seeing. These purple dots reflect the actual ratio that should be if it weren't for this loss or gain. Now, you notice a couple things. One, you're not anywhere close to 47 million years. In fact, in this case, you've made it worse. But actually, a bigger problem with this is the fact that the purple dots now don't fit to the blue line. So you actually moved it away from the blue line. And the blue line, remember, this is a prediction. This isn't an observation. This isn't something that we write up because we want the math to work. We make this blue line because that's the prediction of physics. How about if it goes the other way? What if we lost a bunch of lead or gained uranium? So if you have going the other direction, again, still not anywhere close to 47 million years, but again, you've pushed the data far away from the actual underlying physics. Now, what if there was a combination? If I push this really far, see how far I can go. So I obviously artificially did this. It's okay. You've just lost 99% of the uranium, or you've just pushed tons and tons of lead in. There's lead just pouring into these zircons over the years. You can squeeze it into 47 million years. But again, this blue line is the physics. So if you're saying that these dots are more representative of truth, of reality, then you need to come up with a physical model that predicts this. So Mr. Golden suggested that maybe the decay rate's not constant. Maybe we think the conservation of energy is wrong, which is what Mr. Golden is suggesting. So, okay, well, maybe it is wrong. What can we do then? And we can see, sure enough, look, I got the data to fit within 50,000 years. Holy cow, that's incredible, right? Mr. Golden's right after all. Well, no, because you can see I put 50,000 years in here for this change of the decay rate. Now, I made it 50,000 years because I've been doing these kinds of things a long time, and I know what creationists like to say. I could have made this 50 years. I could say the entire world was created in 1970. Everything before that's just an illusion, and all we have to do is put in a little 70 here, and boom, we have a mathematical model that fits. But why don't we do that? Where did these equations come from in the first place? They weren't just handed down to us. Somebody had to come up with them. Okay, well, what we start with is the observed fact that the amount of decay is proportional to the amount of material. So Mr. Golden had a small piece of uranium, or a small piece of rock with some uranium in it, and it was decaying. Now, if he increased the amount, if he took 2 rocks or had a bigger rock, we would see more decay. This is an observation that we make today in a laboratory, and this is the mathematical equation that represents that observation. Now, if some of you go off to college and take hard sciences, you might take some calculus classes. If you take enough calculus, eventually you'll get to a class called differential equations. And if you do, you certainly will solve this equation and find that this is the general solution. And in fact, it is the only general solution. C and A are constant values because that's how math works. This is not an assumption. This is a fact of mathematics. This is the solution through differential equations. Now, C and A are not determined by themselves by the mathematics. What we have to do is come up with boundary conditions or initial conditions. And so if we say at some initial time we start our clock, we say that's T0, and then we can measure the amount of material that we started with and the amount we have after some time. Then we can come up with these, fill in these equations, or fill in these variables. The only thing we're left with is A. And when we measure everything else, the thing that we're left, we call that the decay constant. This is that negative lambda. So this is how we measure these things in practice. Now, to get those equations that make the blue line, we have to take another little leap. So this equation is the amount of material you have left. So the amount of uranium you have left is here. And if we say that the lead is the amount of uranium you started with minus however much you have left at the end, then you can get this, this expression for the amount of lead. And then since this is the amount of uranium, all you have to do is divide this whole thing by the last value here, and you get this equation. Now, a really cool thing about this, you notice these N0 values disappear because you have 2 here, you can factor that out, and you have 1 down here, and they cancel out. So how much lead did we start with? None, because that's how chemistry works. How much uranium did we start with? It doesn't matter, because that's how mathematics works. So we don't care how much uranium we started out with. If you have a lot or a little, it's all the same. Now, why not use variable decay rates? It turns out that you could actually make an equation that would fit through all those purple dots. You note that some of those purple dots didn't actually fit. Contrary to what Mr. Golden was saying, it's not true that we move those values. In fact, the values that I used for the figure that I made is the raw data. I did not use the corrected data. I used the raw data. Now, I could have made an equation that would fit through every single one of those purple dots, but I didn't. Now, why didn't I do that? Because if we start with the conclusion, we can always make a model that will fit the data. In fact, this is a process called Fourier analysis. I did in my master's program. You can always fit an equation to whatever data you like if you start with the conclusion. But we don't start with the conclusion. In science, we start with an observation and develop a hypothesis and then test. The constant decay rate is a fact of mathematics, not a presupposition. The observation is the proportionality of decay. More uranium means more decay. And this motivates the differential equation. And that equation is satisfied by a constant decay rate because that's how math works. We don't presuppose a constant decay rate. That's a consequence of observation. Now, there are more reasons. So as Mr. Golden pointed out, these equations don't stand alone. Nuclear decays release energy, about 50 MeV for each of these chains, and time is a function of reference. So this is part of Einstein's theory. So if you say that the decay rates are variable, that makes a prediction. If you put an isotope in a particle accelerator, you should expect those decay rates to slow down. Go do the test. Why don't we have those tests showing decay rates slowing down if that's how the universe actually works? At the end of the day, we have to remember these criteria that we use to choose among our models. And I think that that's all the time I have. So, if the claim that the Earth is less than 47 million years old is correct, it demands, again, that all of the hundreds of thousands of scientists from all over the world, all backgrounds, cultures, languages, and religions, that we've all collaborated to deceive the public, or we're just all mistaken. But the truth is really held by this small group of persecuted creationists. And I ask you to reject that proposition. So that's my time. Thank you.
All right, Mr. Golden, you may now respond.
All right, awesome. So I don't think there's a conspiracy, as I said. I think that human beings interpret data according to their framework that they're exposed to. And unquestionably, the framework that I'm proposing is minuscule right now in our culture, okay? But that's why I guess we're having the debate. So I wanted to get back real quick to some more clocks, all right? Because I feel like if Mr. Redwine's interpretation of the radiometric dating clock is correct, then why am I questioning it? Well, that's because I can look at other clocks, okay? And so I've tried to mention some of those in the last time. I'm going to mention a couple more. By the way, I'll go back to the helium diffusion clock, which is right as uranium is decomposing into thorium, which is used to establish a billions of years old date for certain rocks that contain uranium. Those same rocks, if we date them by the rate at which the helium that is produced is escaping, they come up to be thousands of years, okay? So obviously they can't both be right. Some model is deficient. But at the end of the day, you can choose one or the other, okay? And so there's the exact same process, depending on what you're measuring, is giving two very different dates, okay? So I'm not obligated to choose the one that people prefer to use. Why do I say people prefer to use it? Because human beings do the math very quickly, right? If I said, okay, there is no Montana, then you would quickly say, wait a minute, what do you mean there's no Montana? What about the states next to it? What's happening there, right? There's all these other horrible questions that just become ridiculous, right? And so you reject the point of my argument. So many clocks are dismissed out of hand that are quite parsimonious, that are quite simple, if taken at face value, that indicate a young Earth, because if the Earth is less than 47 million years old, then we have to go back to biology, right? We have to undo all of that, okay? We have to look at cosmology again. Mr. Redwine is right. It is an uncomfortable unraveling, right, of the fabric of modern science. But that doesn't mean that those clocks are any less indicative of the true age than any other clock that we could use, okay? So, for instance, I've got a couple of fossils here. These are of extinct squid-like creatures that lived in a shell. This one's just more impressive. This one is actually not datable directly because it's an indirect fossil with the actual creature's not there. But this one is. It contains an aragonite shell, which is calcium carbonate, and the carbon in there can be dated with a technique similar to what Mr. Redwine was discussing, only it's using carbon, radioactive carbon isotopes instead of uranium and thorium, uranium and lead, I should say. And so But with carbon, since carbon has a much faster half-life, that is, its candle is burning much quicker, it's only suitable for measuring things, say, less than 50,000 years of age. Okay, so this rock, this fossil has been dated, I'm guessing 300 million years. I'm guessing this is Mississippian or something if it's from around here. But it hasn't been dated directly. It's just been put into a framework that is informed by a supposed evolution, okay? And we have to have enough time for that to happen. And the surprising thing is, these are not dated very often, because why would you, right? If you already know that this is 300 million years old from the pre-existing framework, you're not going to go through the time and expense of testing it with a method that is only good for things that are 50,000 years or less. And yet, when people do that, they very often get actual ages using the very same methods that Mr. Redwine was discussing, only with carbon. In other words, many carboniferous fossils have been dated and found to be, according to radiometric carbon dating, thousands of years old, not millions. It's the same exact method that he was using to date the zircons. So why aren't those used? Because they're just a rescuing device is invoked, just as I've invoked one for the decay rate, right? We don't see decay rates changing right now. Okay, we don't. So I have to invoke one if I want to question Mr. Redwine's graph. But on these other clocks, similar devices have to be invoked by those who are unwilling to consider the possibility that the Earth could be young because of all the implications that it holds for them. Finally, I did want to look at one other clock, and I debated on whether to use this one, but I'm going to go ahead because I'm knee deep anyway. I might as well go neck deep. If you believe that humanity and the Earth are around the same age, right? And my opponent certainly would not countenance that. But if you happen to believe that, maybe there are some of you that do, then I just want to point out that I think there are many indications that humanity itself is tens of thousands of years old at maximum. Okay, our population growth rates. If you can track the devolution of our language. You can see I'm an example of this. Our vocabulary is increasing, but our sophistication of our language is actually decreasing over time. The mutation load, we're not becoming more vibrant, more fit, more adaptive. We're becoming less so. And thankfully, we have our technology to overcome that. I think a good case can be made that humanity itself is a clock that if you believe that the Earth is fit for humanity, okay? I think there's evidences of that. The fact that we have the Earth is uniquely suited for life. There's water here. There's a magnetic field that protects us, the presence of oxygen, the right amount of gravity, the right distance from the sun, the right temperature. All these things are unique to Earth. We speculate that there's other planets, but that's again an assumption. So if you want to make the assumption that humanity and Earth are linked, then I think you can use humanity itself to place a maximum limit on the age of the Earth. I do want to stop and because I brought up a couple of new things, and if my opponent would like to get the last word, I'd love for him to do that, because I'm really appreciative that he took the time. He was a really coherent speaker, and I think he did a great job.
I appreciate that. I'm sure just a couple seconds even. So one, your claim that language is getting simpler is, you said is simpler or less simple? This is utterly absurd. So I love linguistics. There's a fantastic podcast I recommend to anybody called Lexicon Valley. Go listen to that professional linguist who hosts it. It's fantastic. That is, I apologize, but that is complete nonsense. And actually, more surprising to me was your claim about how mountains are eroding and therefore we should expect more siltation. Are you unaware that there are mountains that are increasing in height? I mean, Mount Everest, the Himalayan mountain range, is uplifting. It actually gets taller every year. I'm not sure where you were going with that, but that's and also, like, you you complained about the decay rates being constant, but then you suggest all of these other measurements of siltation, of increased ocean salinity. Why on earth would you say that the amount of salt going to the oceans is constant? Why would you say that the magnetic field decay is constant? We know for a fact that it's not constant. We can measure historical magnetic field of the Earth, and it does decay sometimes, and it increases other times. In fact, it even changes directions, and we know this. Like, yeah. I don't know. I'm at a loss for words. So thank you for your time. I appreciate it. I appreciate the conversation. Yeah.
Okay, so seeing there are no questions in the chat and questions of my own, I would like to thank all of you who participated today. The recording of this debate will be made available sometime later today, so please contact Dr. Wittenberg if you are interested. Special appreciation goes out to Mr. Redwine, who has made time today to join us from halfway around the world. Thanks again and goodbye.
Thank you.